Hello and welcome. On today's lecture, we will be covering the methodology of puzzle solving. Now, what do we mean by that? Basically, we're going to be covering the methods, techniques, and ways of thinking used to solve puzzles. We're going to be covering both the theoretical side and practical side of this, by using Baba Is You as an example. Of course, any puzzle game can suffice for this, but Baba Is You is the one that's most to the point. And we can cover everything when it comes to the basics. So, who is this meant for? If you're a beginner at puzzles, this may help you get into the right frame of mind for solving them. If you're already adept at puzzles, well, it can still be good to remind yourself of the basics. You may or may not already be employing all the methods here, but formalizing them definitely helps a lot. If you're not into puzzles, hello. Hope you're having a lovely day. If you're not into puzzles, these methods can be used to solve practically any and every problem, due to the way how we are going to be defining puzzles here. That's what I get for doing things unscripted. This can help with puzzles, but it can also help with a multitude of problems that aren't exactly defined as puzzles per se in the traditional sense. So it can come in handy. In fact, I use this all the time at work, if I'm actually feeling motivated for it. So without further ado, let's begin. First, in order to solve a puzzle, we need to ask, what is a puzzle? How do you define what a puzzle even is? Anyone have any ideas? Perhaps the one person that actually sent a message? So basically, a puzzle can be defined as a... A puzzle is something that you don't know the answer to. Close. It is part of what makes a puzzle, but formally, a puzzle can be defined as a state graph. So how do we define our state graph here? So a state graph consists of states. States can be defined with a set of properties. For example, a box is in some location is a certain tile filled out, etc., etc. And actions. Actions modify the state of puzzles. So you go from, say, state 1 to state 2 with a different set of properties of said state. This is how we're going to define our puzzle state graph. There is also a third component to puzzles, and those are the rules, quote unquote, as they say. Rules are basically actions that result in states that cannot happen. They basically prevent us from taking actions that result in certain states, thereby creating an enclosed state graph. So a typical puzzle can be defined as one starting state, a subset of states that are called the ending states, a subset of end states, connected by an unknown set of states and actions that leads from the start state to the end state. And as Aldi pointed out, this is part of what makes a puzzle. Something you don't know the answer to. Now, typically, the solution to a puzzle can be defined in one or two ways: the ending state or the set of steps that takes you from the start state to one of the ending states. Depending on the puzzle in question, of course. Any questions thus far? All good? All good. Okay, so why do we have a... Okay, so one set... Well, there is always only one starting step. If you choose a different starting step, it's going to be a different puzzle. Yep, that's also another reason why I picked this game. There's always one starting step, or rather state. Because if you choose a different starting state, it's going to be a different puzzle entirely. The ending state is defined by a specific set of properties, typically. So yeah, let's say an ending is defined by property 1 and property 2. There can be a multitude of states that can fulfill property 1 and property 2, thereby making them in the set of possible ending states. Of course, if n equals 1, the number of ending states equals 1, that means that the puzzle is uniquely defined and only has one solution. At least in typical puzzle terminology. A practical example of this would be, let's say, in Tetris, you have a starting state of a completely clean board. You can choose to place pieces in whatever way you choose to. Let's say the objective is for the board to have 100 cleared lines. So you can place pieces however you want to, leading to a variety of states. However, all the states at the end which have 100 lines cleared can be defined as a proper solution, or ending state. Okay, next we are going to be touching upon the classification of puzzles. So, puzzles are classified depending on the properties of the end state. So, puzzles can be either with closed end states or open end states. So what do we mean by this? A closed end state is defined by a set of properties that influence prior steps. For example, let's say that you need to get to a flag. This is the puzzle. In order to get to the flag, you need to create a pathway. So let's say we have a closed door in the pathway. That door needs to be opened due to the ending state requiring us to be at the flag. So information about the end state can be propagated backwards through the puzzle in order to give us more information on how to solve it. Compared to, let's say, an open end state of a puzzle, let's say a Sudoku. The end state of this puzzle can be defined as all the fields are filled out. Does this give us any information to help us deduce which numbers can go where? No, it does not. Information about the end state cannot be propagated backwards. It cannot be used to deduce what steps are needed to take in order to actually fill this out. Of course, it's not all cut and dry like that. It's not exactly a hard restriction, whether it's not closed or open. It's not binary, it's rather more like a spectrum, depending on how much the information can be transmitted backwards or not. Sudoku is great for keeping your brain active. Sudoku is great for one type of puzzle solving, and that is forward propagation of actions, rules, and states. Sudoku break training ideas? Nice. You should try some of the more advanced puzzle Sudokus in that case. I recommend a channel called Cracking the Cryptic. They do some fun Sudokus there. Now then, as I was saying, we have closed and open states that is more like a spectrum. Hello Greg, hope you're having a lovely day. Please be quiet. We are, well, you can really ask whatever questions you want regarding puzzles. So. Oh dear. Let's clean this up a bit. Alright, so puzzles can be open or closed in a spectrum. Another way of viewing this type of spectrum is the P versus NP problem. Is anyone here familiar with P versus NP? Probably not. Well, P versus NP basically defines a set of problems P, which is a subset of greater problems NP. Basically, the problems in P can be solved incredibly simply. Basically, if you want to check a solution, it is the same complexity as reaching it. But the question is P equal to NP? Because if so, basically every puzzle in the world becomes trivial. Of course, P is not actually equal NP. I'm not sure why it is even such a problem. And that is simply because of the lack of information transfer and propagation backwards, or rather the loss of information as you take actions through states. Okay, now we get into actually solving puzzles. So, how does one solve puzzles? So, first of all, to solve puzzles, you need to know these in-between steps. How to reach the appropriate end state. So, this subset of states and actions is at first unknown. So, the first step to solving the puzzle is the so-called rule discovery phase. For example, you take an action from one state to another and see if it works. If it does, great, that is a legal action. If you take an action to another state, but it doesn't work, no can do. Ooh. This pathway is sealed off. You cannot do that. You have discovered a rule. So yeah, these rules can be either explicit or implicit. Typically, explicit rules on puzzles are stated in the, let's say, instruction manual for the puzzle. That is the case for a lot of puzzles. Sudoku has predefined rules and other rules predefined, so it's as easy as just reading those rules. As far as explicit rules are concerned, implicit rules basically imply a combination of actions that lead to a dead end. So let's say, for example, you want to fill out a grid. The basic rules are all the white tiles are connected and all the dark tiles are connected. Those are the explicit rules, but an implicit rule that can be derived from that is, for example, if you have this configuration, this cannot happen because it makes the connection of these two and these two impossible. This is an implicit rule. Implicit, so you can basically cut off a lot of the possibilities in the tree here right off the bat. This is where all the special techniques for solving different types of puzzles come from. It's all the implicit rules that come from the explicit ones. Almost like math? It is, in fact, math. Anything can be reduced to math, really. Math and logic. Okay, so now that you understand the rules, what actions you can take to result in valid states and what you can take to result in invalid ones, you can end the rule discovery step and begin the rule application step in order to construct steps that take you from the starting step to the end step. Based on the rules, you try out things, see if they fit in within the criteria of the rules and the ending state, and proceed from there. The closer you get, the chances are you are most likely correct. Okay, any questions thus far? Nope, we're all good then. So, now we know how to construct the puzzles. What are the methods you can use to construct the solution from the starting step to the end step? What do we use to most efficiently construct this? Well, there are three primary methods to take. First one is experimentation. Second one logical deductions, and the third is intuition. These are ordered by efficiency from least efficient to most efficient. Experimentation is commonly referred to as brute force. So you basically take the starting state and do every possible action. And see the ones which can yield positive results. This is, of course, extremely effective during the initial rule discovery phase. Is brute force good? Yes. Yes, it can be. It's always the one thing to fall back on. Just try everything. Even if you don't think it will work. Speaking of which, what makes you think some things will work and some things won't? That would be logical deductions. So basically, if you start from a state and you know the rules through experimentation or just reading them, you know already to eliminate every possible action that does not result in a valid state, and can choose from a subset of various states that does, in fact, advance you towards the solution. Of course, for this to be true, all the information you have must be correct. How do we know what information is correct? Well, we will see in the practical section once we actually do the puzzles. Third way, and the most efficient way of solving puzzles, is intuition. Intuition is built up as you do puzzles. So basically, you have a starting state 1. You can take an action 1 or 2. You know action 1 is a valid one. However, if we take, say, action 2, you will know it's invalid based on prior knowledge you have acquired. So basically, you know a rule, A3, that works similarly to A2. You can intuit that it might also work the same in terms of leading you to the end state. This is most commonly done in terms of implicit rules. So you can preemptively cut out plenty of things. Okay, that's it in terms of the theoretical side. Everything else will be explained practically. If there are no questions, then we may begin. Okay, everyone is ready, so we can actually begin solving the puzzles using the methods described. Now then, rule discovery happens even as you begin. So pay close attention to what is happening. What is this? This is how you solve puzzles. Now, pay close attention, because if you think in the way that I'm about to show you, you can solve practically any problem. So, if you pay close attention to the cutscene, you will notice that first the word appeared, then the corresponding object appeared afterwards. Same goes for all the words here. So we can assume that this is consistent. The words presented here define which objects are present within our current world. If you want to be poetic about it, you can say that in the beginning there were words, and the words made the world. Next, we get some additional words which form sentences based on, well, let's say basic intuition. We also have explicitly defined rules here. Could this also be an explicitly defined rule? Let us experiment. If we press the arrow keys, we indeed can move. So you, in this case, can be referred to as you, the player. Next we have wall is stop. So let's see, when we try to move into the wall, we cannot. We have rock is push, we move into the rock and we push it. Now then, what do we know from this? When it comes to the rule discovery process, we need to very explicitly separate what we know for sure and what we assume. So, what we can be absolutely sure of is that an object that is U cannot move into an object that is stop. This is the only thing we know for sure. If you want to know what you know for sure, always reduce it to the utmost minimum of what you have tried. Do not let any assumptions cross over. An assumption would be that anything cannot be moved into something that is stop. And this is only within the context of that being the only things defined. The only things defined is stop and U. Other things may also influence this state, so this in a vacuum is the only thing you know for sure. So, let us try pushing something that is push into something that is stop. It does not work, so we can make our assumption stronger here. Now, all this is pretty basic. However, it is precisely the most basic things that you need to train this way of thinking on. Okay, next one we have flag is win. Now then, we can assume that this is the end state. Okay, so an object that is U is overlaying the object that is win. We win. And that is the only thing we know for sure here. Everything else is assumptions. Now, is having assumptions good? Yes. Good assumptions, more often than not, tend to become true. And you can use them to more efficiently solve puzzles. Good assumptions are based on good intuition, and good intuition is based on good training. Good observation, knowing exactly how things work and being able to accurately deduce how similar things may also work. Okay, next puzzle. Okay, we have clearly defined words here, but they are arranged vertically now. So, we know we can spell out things horizontally and vertically. We also notice these things are disconnected, but also slightly faded out. Alright, time for a little rule discovery. Okay, because wall is stop, we cannot go anywhere past here. The only object we can interact with is this. This is what we know for certain. And would you look at that, we can move text around. So now that this is grayed out, let us build the assumption based on the presented information up here. The flag wasn't sparkling because these are disconnected, so we can move through the wall. Quite challenging. You may laugh at the basicness of this, but you'll see what happens once we employ these basic methods to quite a bit more complicated puzzles. The basic ones are the ones that you need to drill into your mind. So we know we can move text, and we know we know our end conditions based on what we have learned from the previous puzzle, and we can use that to solve this one. Okay, so what is this puzzle trying to teach us? Well, this is basically trying to teach us what we already knew. Words define the objects that exist. And the properties define which properties objects in the puzzle have. But basically, what object has which property is entirely irrelevant. The objects may as well just be decorations. What is important is the properties which are attached to them. Okay. Next, we are going to be introducing logical deductions. Any questions about the discovery step thus far? Okay, I'm gonna assume no, so we can proceed into introducing logical deductions into the mix. So, first of all, let's see, do we have anything that is unknown here? Well, we have a property that is unknown, and that is the sync property, so let's experiment with it. Okay, so what we know for certain is if an object moves into an object that is sync, both get eliminated simultaneously. Well, we know that an object that is U is an object that sinks. This is an assumption. Any object is an assumption. So let us test our assumption that it's actually any object. For example, these rocks can be pushed. Okay, so we know it's an object that is either U or can be pushed into the water. This makes our assumption a fair bit stronger. Now we add in a logical deduction to the mix. So, this is our starting state. We have one baba is U, and two rocks that can be pushed. This is our starting state. These rules are immutable since we cannot reach them. Our only course of action is to go through this puddle of water. So, because of how sync works, based on what we know, either an object that is U or push can be sank, we can sink one object. Do we sink the baba? No. Because we need to be U to control a thing here. So we instead sink a rock. This brings us to the next state. We now have two objects at our disposal, one baba and one pushable rock. In order to get through here, we need at least two objects. So because of the flag is win condition, an object that is U needs to be on top of an object that is win, which means we have one object and one object, a total of two objects. 2 minus 2 ends us with the flag, which is only one object. So this does not work. So we can eliminate this. Might as well showcase that we eliminated this. Our only other interactable items here are rock is push and flag is win. So we only have two objects left at our disposal. Because we only have one baba and one rock, those two are the ones that have to be overlaid. And because we know from a previous puzzle that object definitions are what they actually are is hugely irrelevant. What only matters is their function. So we can instead, whoops, wrong way. Make the rock be the win object. And there you go. We didn't even actually need to do anything in the game. We solved it purely through logic. Is this process incredibly slow? Yes. It is when you have to explain every detail of it, but this kind of detailed thinking is precisely what you need to build up to do subconsciously. And it's easiest to do it on simple puzzles, which is what we're doing right now. Okay, so next puzzle. Same old steps. Do we have anything that is unknown here? Well, we have this new property, is defeat. Skull has this property. What happens if you move into it? Okay, so what we know for certain is you get eliminated if you are on top of defeat. Okay, let's experiment a little. Let's see if other objects get destroyed. No. No, they don't. Hello, Marty. Don't worry, you're right in time for the practical section of the class. Yes, this is what we know for certain. Okay, so what we know is for certain that push into defeat is a-okay. So, a safe assumption here would be anything that is not you into defeat is okay. Now, the only pathway up through here is through these rocks. Rock is defined as push. So, what we are forced to do here is push two rocks simultaneously. Now we can add something more to what we know. That objects that are push also push. So we can assume that anything that goes into an object that is push can in fact push it forward. These are reasonable and strong assumptions to have. Of course, keep in mind, these are still just assumptions. If you ever run into a problem that contradicts your assumptions, you need to go back to experimenting. Okay, so because flag is win is... because these are immutable, we need to bring Baba here onto this flag here. So in order to do that, we need to cross this pile of skulls. So that means that we need to disable this property first before we can proceed safely onto the flag. We have already established that an object that is pushed can safely go through an object that is defeat. So we can use that. Next is also an object that can be pushed, so push that and we can safely disrupt this text and win. Now, a lot of things you come across, things that you know and you assume, depending on how complicated the puzzle is, it can get a bit overwhelming, so taking notes might be a good idea. Okay, next up, volcano. Alright, let's speed things up a little. Okay, so we start here. We are enclosed within this space, so the only thing we can interact with is this here, and we need to get past this. We learned that push is a transitive property, so we can move this out of the way without disrupting it. Rock is push, so we can easily get out. Okay, next up we have an unknown here. Lava is melt and lava is hot. Okay, so let us assume that this defeats us, so let's experiment. Boop. Okay, so we know for certain that melt disappears but hot remains, so that is an interaction. Okay, it does not melt things that are not melt. So we need to cross this lava to get to this flag because, well, this property is immutable. And if we already get to the win, we can already get to the flag. So how do we cross this? Well, we have the lava keyword here, so we can add properties to it. So the question here is how things interact. This is still experimentation, so the idea is if you use push to push lava, it will not melt you. That was an assumption, and our assumption turned out to be correct. This one, not worth doing. Okay, so what are the rules here? Well, grass is stop. We can assume that this is grass. And lava is you. Okay, so we need to create flag is win. Because grass cannot have additional properties added onto it because it's blocked off here. And we need two objects, so it cannot be Baba. So it has to be that flag is win. So we are missing an is here. Where do we get it from? Well, we cannot put anything here, so the only other is remaining is this one. And because we know, even from this puzzle itself, that statements can be written both vertically and horizontally, we can attempt to use this is. It's better here. And our hypothesis turned out to be correct. So what we have learned is that is can be used in multiple statements simultaneously. So what we can assume is that the same can be applied to all words. They can be used in multiple statements simultaneously depending on how you build your rule structure here. Okay, any questions about applying logic thus far? I'm going to assume that no, there is not, so we can move on to the next step. What we have been doing thus far is known as open puzzle solving. If you remember at the beginning in the theoretical section, puzzles were divided based upon the information the end state provides us. Closed puzzles and open puzzles. Now, closed puzzles can be solved as open puzzles, but open puzzles cannot be solved as closed puzzles due to the lack of information that can be propagated backwards through the states from the end state. So, because Papa is U is a closed end state type of puzzle, we can apply the following type of logic. Working backwards. Now, when people say working backwards, they typically mean from the solution, because the solution is a closed state with certain properties. Of course, this is a specialization of a more general rule, that is, looking for choke points. The end state itself is a choke point because it contains specific properties of a state that have to occur. Just like other choke points can contain other specific properties. So, first of all, do we have anything that's unknown? Well, we have our first conjunction, and so we can assume that we sink the object that we touch, and indeed it is so. We experimented and we found out. So, let's start solving from the ending here. The ending is a choke point, because this is an immutable condition. This is also an immutable condition. Okay, this one is not relevant. When looking for choke points, it's good to understand exactly what the state scope of influence is of each rule and property. So for the ending here, what influences it is just these jellyfish. So, to get to the end, we must cross this jellyfish. So we have to get rid of it, because it will sink the object that is U. For us to do that, we need to push an object into it. So let us assume that any object pushed into the jelly will sink it. Well, how about this? Let's take this word and push it into the jelly, so that we may be able to cross. Okay, working backwards, in order to access this, we need to get across this block of ice, which we cannot do because we are sinks, so we need to disrupt this rule and we are free to access it. So that is the solution. And we solve it entirely working our way backwards through choke points. This is especially useful in case you have a lot of possible open states that you can transform to. Now, a very common problem when it comes to these closed type of puzzles is overthinking. You have so many options available to you that if you start working from the end, only one actual path becomes clear. Alright. Next closed state solution. So, we have that which is u here. Because the wall is stopped, we are enclosed to acting within here. So, this is an immutable condition, and once we reach here, is when. So this is our end state. So what we know is that object that is u has to be touching the object that is when. Do we have any words that pertain to objects outside of the boundaries of the wall? The only one here is crab, so you have to use this guy, turn it into u, in order to be able to reach this. So how do we turn this into u? Well, this is immutable. We know conjunctions from a previous puzzle. We weren't actually able to experiment with the conjunction, but if it works with properties and to achieve multiple properties on the same object, let us safely assume that it can also work with object definitions itself. So this has to go there. Okay, what is in the way to get this there? Let's see, we have a skull and a star. Skull is the feet. So an object that is u cannot pass and needs to be pushed, so this guy needs to be eliminated. Star is sink. Well, we have an option of eliminating the skull with the sink method because we know it removes an object. Would you look at that? Star is sink. Star is already sink, so we can use that. We'll need to get the star to the skull, so we use his push. Going by our prior assumptions, let us assume that we can turn this and use star in multiple statements simultaneously. Okay, in order to actually reach this place, we need to get past the rock that is pushable, which isn't a hindrance. And there you go. That is the solution. So let's just test our little hypotheses here. Works. Indeed it does. Let's make a little space. There we go. And then we simply move on to the ending. Solved entirely backwards. Let's see. Okay, another practical example. This is immutable, so this is the end state. We need to get an object that is u here, past the immutable defeat. Well, since... just a second, I need a glass of water. Now then, we need an object that is you in here to overlay with the flag, which means it needs to cross the immutable defeat. So we know that an object that is not you, well, we don't know. We can assume that any object that is not you can safely pass. Not you, and then it turns into you pass here. This is a logical deduction. This is the only possible way, based on what we know, to get an object that is you past something that is defeat. So we need something that can be changed. Well, is you is mutable. And the only other manipulable object, well, the two manipulable objects are pillar and wall. Technically, we can use either one of these. Let's use wall just to be fun. Of course, it states that pillar is push, but we can just make wall is push as well. And then push this wall that is not you through here. Ah. No, we cannot. Because the wall needs to be is you at the end. Okay, thankfully I cut that line of thinking short. A little forward thinking there. So it has to be pillar. So you gather up a bunch of these, push them through. And then you take the word pillar and turn them into is you. And we can safely win. Any questions about closed solving of puzzles at this point? If there isn't, I am going to add a little something to the closed solving of puzzles because it doesn't quite capture everything we are about to do these couple of puzzles here. So, closed solving of puzzles involves choke points, the types of properties that states need to have. So, let's say, for example, we have a hallway here. Our objective is to get past a closed door here, and then afterwards have the door be closed again. So what needs to happen is the door opens and then closes behind us. The choke point here is that for us to be at the other side of the door and it to be closed, this is the choke point. So if you're constructing a mechanism that opens the door and closes it behind you, what needs to happen is a guaranteed state in which the door is open. Everything else afterwards has to be built on top of this choke point state. Okay. Next. We are going to be talking about going back on things we know. So sometimes you may be incorrect in what you do and don't know. So what we thought we know is an object that is you has to be overlaying an object that is when to reach the end. However, you need two objects for this. We cannot have two objects interact simultaneously due to this. This cannot be reached. This wall cannot be crossed, so these objects are completely independent. So we need only one object. So let us turn our thinking a little. So the object that is you has to be overlaying the object that is win to win. But what is also happening is that they are both on the same tile at that point. So what needs to happen instead is that you and win have to be on the same tile. Of course, this is just an assumption. So let us test if that theory holds true, because this is the only way our current theory fits into what was happening previously. And indeed it was. Now we know of an additional way to, well, not an additional way, but rather the true end state. The object of you and the object of win need to be on the same tile. If they are both the same object, the you and win condition are on the same tile, meaning you win. Revision is key. Whenever you're presented with new information that contradicts the previous one, the best revisions are done when the information you have gathered gets to be put into a different context, but still makes sense in the old one. Okay, let's see. Any questions thus far before we move on to the final lesson when it comes to the basics? Assuming no questions, we can proceed on to meta-knowledge. So what is meta-knowledge? Meta-knowledge is using knowledge outside of the puzzles themselves in order to help complete them. Or, as plenty of people like to call it, is complete and utter cheating. So, let us look at our current state of the map and see our puzzles here. We have a cluster of puzzles defined here, cluster of puzzles defined here, and a cluster of puzzles defined here. So what does this mean for us? On the macro level outside of the puzzles, we can see that the puzzles are grouped. Grouped by what? Perhaps a common property that unites them. So perhaps we can use a bit of this knowledge to help us progress through some of the later ones in these groups. Of course, we also know these puzzles are numbered. And it would be wise to just follow the ordering. Good game design only teaches you everything you need to know in controlled environments. Things you can deduce yourself, you can safely do so because, well, it's a controlled environment. In fact, that's what I've been using this entire time in order to construct this lecture as a puzzle using the meta-knowledge of game design. Okay, we're gonna do a little prerequisite here. This log puzzle. Okay, we're gonna solve it very quickly, using the intuition and knowledge built up from previous puzzles. So we have an unknown shut and open property. Okay, let's assume that open opens shut. Okay, those objects disappear. We assume anything that is open opens that is shut. And because the door is additionally stopped, let us assume that shut does not also mean stop, so we can safely go through it if it's not. Okay, let's work our way backwards. In order to get to the flag, whoops, this one. Okay, in order to get to the flag, we need to go past this door. We need one object to open this, one. Okay, we gain +1 object to manipulate here. -1 object to open this door. Okay, +1, the key here, and +1, -1. So key, and then rock to open. Okay, we focus now on this group of puzzles, specifically. Okay, this one is trying to teach us a new property. Well, another way to manipulate objects, because wall is defeat, we cannot cross it, we cannot manipulate anything outside of the boundaries, so we need to get rid of the wall. The only things we can do is stop, or through a little experimentation, cannot be as is, found out that objects can be transformed into other objects. And from knowledge of a previous puzzle, we know that everything else is relevant, and just getting out here is the end state. So our first puzzle introduces the forced concept of x is y. Okay, so here we have another x is y situation as we suspected. So let's change it back. Of course, we cannot. Because rock is rock. This is the only other statement which affects rock, so if we break it, and there we go. So rock is unchangeable if x is x. So this is what the meta-knowledge we have over this cluster of puzzles thus far. Transforming objects and immutable objects. Okay, here it is used once again as a restriction. We need to get to this jelly, but that is impossible because flag is stopped, so we need to think a little differently. Well, let us use the meta-knowledge and transform an item. Flag cannot be mutated anyway. Another form of meta-knowledge is what you have available to you. For example, why is this particular section open? It's all about the observation. Well, if we transform you here, we can get into a state where we can break this. And also, there is a suspicious little empty space here. The meta-knowledge here being that we can definitely transform something into something else into is win. So let's just grab the flag and solve it that way. Right, so the meta-knowledge we have over this cluster of puzzles is it pertains with x is x and x is y in terms of object transformation. So we can safely assume that this next puzzle is also going to pertain to this. So our objective here is to get something is win. Let's test out the property of defeat first. Can we simply make Baba is win? No, because an object that is defeat and an object that is you that are on the same tile causes you to be defeated. Same way as win. So, using our knowledge here of available objects, we only have flag, Baba is you, Baba cannot cross, based on what we know, flag cannot be moved, so it has to be crab. But then, when we pass through here, we get Baba is crab, and Baba will be a crab, and we will be no more. So, using two pieces of meta-knowledge here, for example, why is this hole in the wall suspiciously open? Why is this Baba available to us? And the fact that this cluster of puzzle is related to x is x in order to have objects be immutable, we can construct Baba is Baba in order to safely get Crab across. In order to do that, we need to open this door, grab the available is, and safely push it through. Because it's negated due to our prior knowledge. And we use meta knowledge to easily and quickly construct a solution of this puzzle. Like I said, this is basically cheating. All the knowledge you have is available to you, but you can take lots and lots of shortcuts if you know how games are constructed, how puzzles are constructed, and even in some cases, what the author is like, what he likes to do in his puzzles. And that is basically everything about solving puzzles. The basics at the very least. Yes, these puzzles were extremely simple, but these simple puzzles are precisely the ones you need to train yourself on when it comes to using these methods. It's important to learn how to think in this way. Yeah, as with most anything, it all comes down to training. Of course, you can in fact use this knowledge I presented to you here to solve any puzzle out there. Literally anything. It's going to be very slow, because you need to train yourself in solving specific kinds of puzzles due to the implicit rules of the puzzles. But it can be done, using just what I presented here. From the simplest to the most complicated one. Well, looks like nobody has anything to say, so we will be wrapping up for today. I'd like to thank you all for watching, and I'll see you again in potentially other lectures. When do we learn the art of the origin of Hedgehog? I mean, if you want, I can give a lecture stream about Sonic the Hedgehog if that's what you would like. Sonic's origins can be reduced to a puzzle, and it can be logically deduced, much like anything else. Keep going, what? You want a bonus lesson about the origin of Sonic the Hedgehog? Stream is too short? I mean, lectures are typically up to an hour long. This was a bit of a longer one. Like I said, most of the preparation for this, well, most of the time for this stream came from the preparation. I mean, look at this. See that? I can freely draw on stream now. Can easily point out things. You are learning. Okay, fine. Okay, fine, but it's not going to be the stream. It's going to be a separate stream. And I'm going to stream it only on Twitch. Sound good? No, I mean, I'm going to end this stream and start a new one immediately. Yeah, immediately. Just separate the lesson from the bonus stuff. Alright, fine. Alright, if you want to continue watching this playthrough, and to get a bit of insight into implicit rulings when it comes to solving specific types of puzzles, you can go here. Wow, it doesn't actually show up properly in this thing. Ah, well.